Magnetic properties of electrons. Electrons generate magnetic fields due to their charge and spin, leading to different types of magnetism in materials. 1. Magnetic moment of an electron. The electron spin creates a tiny magnetic dipole moment. The orbital motion of electrons around the nucleus also contributes to magnetism. The total magnetic moment depends on both spin and orbital angular momentum. 2. Types of magnetism. 1. Diamagnetism, weak repulsion, occurs in materials where all electrons are paired, for example, noble gases, water, copper. These materials repel an external magnetic field. 2. Paramagnetism, weak attraction. Happens when a material has unpaired electrons, for example, aluminum, oxygen. These materials are weakly attracted to a magnetic field but don't retain magnetism when the field is removed. 3. Ferromagnetism, strong permanent magnetism. Found in materials like iron, cobalt, and nickel. Unpaired electrons in atoms align in the same direction, creating a strong permanent magnet. These materials can retain magnetism even after the external field is removed. 4. Antiferromagnetism. In some materials, for example, manganese oxide, adjacent electrons have opposite spins, canceling out the overall magnetism. 5. Ferromagnetism. Similar to antiferromagnetism, but the opposing magnetic moments are unequal, leading to some net magnetism, for example, magnetite, Fios. 3. Spin and quantum mechanics. Electron spin alignment is key to quantum computing. Qubits use electron spins for data storage. Spin-orbit coupling affects atomic spectra and electronic properties in materials like semiconductors. Energy levels and orbitals of electrons. Electrons in an atom exist in discrete energy levels shells and occupy atomic orbitals based on quantum mechanics. 1. Energy levels shells. Electrons are arranged in shells n equals 1, 2, 3, where n is the principal quantum number. Each shell has a fixed energy and can hold a maximum number of electrons. N equals 1 gives 2 electrons. N equals 2 gives 8 electrons. N equals 3 gives 18 electrons. N equals 4 gives 32 electrons. 2. Atomic orbitals. Within each shell, electrons are distributed in subshells with different shapes. S orbital gives spherical holds to electrons. P orbitals gives dumbbell-shaped holds 6 electrons. D orbitals gives complex shape holds 10 electrons. F orbitals gives even more complex holds 14 electrons. 3. Electron configuration rules, off-bow principle. Electrons fill the lowest energy orbitals first. Pauli Exclusion Principle. No two electrons in an atom can have the same set of quantum numbers. Hund's rule. Electrons occupy orbitals singly before pairing up in the same subshell. 4. Energy transitions and spectra. Electrons absorb or emit energy when they move between energy levels. Absorption. Electron jumps to a higher level by absorbing energy. Emission. Electron falls to a lower level, releasing energy as light photons, forming an atomic spectrum, for example, hydrogen emission lines. Wave-particle duality of electrons. Electrons exhibit both particle-like and wave-like behavior, a fundamental concept in quantum mechanics. Evidence of wave-particle duality. 1. Particle nature. Electrons have a definite mass 9.109 times 10 kilograms and charge 1.602 times 10 C. They can collide with other particles, be detected individually, and transfer energy in discrete amounts quanta. 2. Wave nature. Double-slit experiment. When electrons pass through two slits, they create an interference pattern behaving like waves. Electron diffraction and de Broglie wavelength. Louis de Broglie proposed that moving particles, including electrons, have a wavelength, where h is Planck's constant, m is mass, and v is velocity. Electron microscopes. Electron waves allow for high-resolution imaging, surpassing optical microscopes. Implications. The wave-particle duality is central to quantum mechanics and quantum computing. It leads to phenomena like quantum tunneling, electrons passing through barriers they classically shouldn't. Electron spin. Electron spin is a fundamental quantum property similar to angular momentum but intrinsic to the electron itself. Key properties of electron spin. 1. Spin value. Electrons have a spin quantum number s of 1/2, meaning they can exist into spin states. 1/2 spin up, 1/2 spin down. 2. Quantum nature. Unlike classical spinning objects, electron spin is purely a quantum mechanical property. Electrons do not physically rotate. 3. Pauli Exclusion Principle. No two electrons in an atom can have the same set of quantum numbers, meaning electrons in the same orbital must have opposite spins. 4. Magnetism. The electron spin is responsible for magnetic properties of materials. Unpaired electrons lead to paramagnetism and ferromagnetism, while paired electrons cause diamagnetism. 5. Spin-orbit coupling. In atoms, spin interacts with the electron's motion orbital angular momentum, affecting energy levels and causing fine structure splitting in atomic spectra. The mass of an electron is 9.109 times 10 kilograms or 0.511 MeV/s². Key points: extremely small. It is about 1/1836th the mass of a proton, making electrons much lighter than protons and neutrons. Influence on motion. Due to their low mass, electrons move very quickly, especially in atomic and quantum systems. Effect on chemical reactions. The small mass allows electrons to be easily influenced by electric and magnetic fields, making them essential in chemical bonding and reactions. Relativistic effects. In very high-speed conditions, for example, in heavy elements or particle accelerators, electrons exhibit relativistic behavior, affecting their energy levels and interactions. Electron charge. Electrons have a fundamental negative charge of -1.60 to 10 coulombs. This charge is exactly equal in magnitude, but opposite to the charge of a proton plus 1.602 times 10c. Why is the electron's charge important? 1. Electromagnetic interactions. Electrons interact with other charged particles via the electromagnetic force. This force is responsible for electricity, magnetism, and chemical bonding. 2. Atomic structure. The negative charge of electrons is what keeps them bound to the positively charged nucleus in atoms, forming stable structures. 3. Electricity. The flow of electrons in a conductor creates electric current, which powers electronic devices. 4. Charge conservation. The total charge in a closed system remains constant. Electrons may transfer between objects like in static electricity, but their charge does not change. 5. Quantum electrodynamics cubed. The electron's charge plays a key role in quantum field theory, influencing how particles exchange forces via photons. 1. Charge. Electrons have a fundamental negative charge, equal in magnitude but opposite to the charge of a proton. This charge influences electrical and magnetic interactions. 2. Mass. Though extremely small, the electron's mass is crucial in determining atomic and molecular structures. It's about 1/1836th of a proton's mass. 3. Spin. Electrons have a quantum mechanical spin of 1/2, meaning they can exist in two states, spin up plus 1/2 and spin down 1/2. This property is key in quantum mechanics and magnetism. 4. Wave-particle duality. Electrons behave as both particles when measured and waves when unmeasured. This duality explains phenomena like electron diffraction and quantum tunneling. 5. Energy levels and orbitals. Electrons exist in quantized energy levels around the nucleus. These levels are divided into orbitals s, p, d, f, and an electron's position is described by four quantum numbers. 6. Magnetic moment. The movement of electrons generates a tiny magnetic field. In some materials like iron, electron alignment results in ferromagnetism. 7. Pauli Exclusion Principle, no two electrons in an atom can have identical quantum numbers, which governs atomic structure and chemical bonding.